make a short introduction. Good afternoon and welcome to our seminar in optimization. Our speaker today is Patrick Mehlitz from University of Brandenburg, Cottbus. Patrick received his PhD in 2017 from the University of Freiburg under supervision of Stefan Dempe. And after spending another year in Freiburg, he moved in 2018 to Cottbus, where he is member of the research group of Gerd Wachsmuth. Patrick has a very wide research profile. He's working on topics, let's say, with a strong theoretical character. It's working on topics in osmotic optimization, on bi-level programming, on stationarity conditions, on optimality conditions. But I noticed in the last years an increasing interest in numerical methods in optimization. And I guess that today's talk will be, let's say, a combination of these two main components of his research. Yeah, it is correct, Patrick? Yeah, let's see.
Everything correct, very fine. Yeah,
so, you have 45 minutes for a talk, so the floor is yours.
Thanks very much for the introduction, Radu, and yeah, thanks to the organizers for giving me the opportunity to give a talk here at the seminar. And yeah, as Radu already announced, this talk will be a mixture somehow of some theoretical foundations and numerical applications. And I will speak about optimization problems with geometric constraints. And in this framework, which is quite general, I will speak about so-called asymptotic stationarity and regularity conditions, or conditions, and their application in numerics. And yeah, this will last, I think, about 35 minutes. And the last 10 minutes, I will speak about extensions of the theory to different branches. So where we can find some generalizations of this theory and how can it be used in different areas, optimization theory and numerical practice. And that is why I present this longer list of co-authors at the bottom of the slide. So this overall research project on asymptotic stationarity and regularity is based on joint work with Matushpenko, who is now in Vienna, Christian Kanzo from Würzburg, Alex Kruger from Ballarat, and Gerd Wachsmuth from Cottbus. So after a brief introduction, I will speak about these asymptotic stationarity and regularity conditions. So what does this mean? Where it can be used? How is this related to standard notions? Then I will speak about a safeguarded augmented Lagrangian method, which can be used to solve geometrically constrained programs. And the convergence analysis will be briefly presented, and I will highlight where these asymptotic conditions come into play. I will speak about numerical results and some related works at the end of the talk. So what one has to say, this interest in asymptotic notions of stationarity and regularity for standard nonlinear problems somehow started in 2010 or some years before in South America in the research group of Roberto Andriani, who introduced this for standard nonlinear problems. And then this overall theory was generalized up to the degree we have today. And the interest in these tools is due to the fact that they provide quite general stationarity conditions holding in the absence of constraint qualifications, and that these asymptotic regularity conditions resulting from that are quite weak constraint qualifications, which apply in the convergence analysis of different methods, for example, SQP, relaxation methods, or as I'm speaking about today, in multiplier penalty methods. So that's quite a general thing. And without further words, I'd like to start into the topic. So the problem we want to investigate here is a problem with geometric constraints, which means we minimize the scalar objective function f defined on some Euclidean space X, so finite dimensional Hilbert space. And the constraints, there are two types of constraints. The first one is g of x and k, where g is some smooth mapping to another Euclidean space y. And we have there the k, a closed and convex set. These are nonlinear constraints, but we treat them as not to be too difficult. And then we have another constraint, x and c, of abstract type, and assume that the c is somehow challenging. So some challenging variational type with a challenging geometric structure. And that is why we call this problem problem with geometric constraints and denote the feasible set of it by a calligraphic F. Okay, so some examples where this pops up. A very easy situation pops up if C is a closed convex cone. For example, the whole space, then we have just nonlinear constraints of set type. Okay, but there are also more challenging setting. I think all of you know, for example, if X is the set of real symmetric matrices, then we can choose C to be the cone of semi-definite matrices therein. And then we are in the setting of semi-definite programming, popping up, for example, eigenvalue optimization, matrix inequality constraints, arising from example from applications in communication theory or experimental design. And another very popular setting is the one of second order cone programming, where C is second order or ice cream cone. And this frequently arises, for example, when reformulating probabilistic or robustified constraints. So we have applications in conic optimization. Another interesting setting pops up if C is the union of finitely many convex polyhedral sets. This is of particular interest here, and we call this setting the setting of disjunctive programming. And there are many classes of disjunctive programs some of you might be aware of. For example, these guys here. We have, at the first glance, I think everyone knows this, mathematical programs with complementarity constraints. So we have non-negativity and perpendicularity constraints on certain functions in a standard nonlinear program. Another interesting situation, maybe less well known, is mathematical programs with vanishing constraints, second case. And for example, logical constraints are also somehow disjunctive. For example, if you consider OR constraints, so one of two inequality constraints has to hold. And what I did here at the bottom of the slide is I just made little pictures of these three types of constraints, and what all of them have in common is we have some large non-convexity there, we have some combinatorial structure, and the feasible sets of these programs are close to crumpling into disjoint parts, so potentially close to be disconnected, and the feasible sets have kinks. So yeah, we are in the setting of non-smooth problems in some sense. And in the standard NLP reformulation, these problems are somehow very low regular. So standard constraint qualifications generally do not hold for these problems. And we are in trouble with optimality conditions and solution methods, for example. A particular setting in disjunctive programming is the one of so-called cardinality constraint programming. There, the space X is just the Rn, and the set C is given by the sets of all vectors in Rn, which have at most kappa many non-zero entries, where kappa is some constant between 1 and n minus 1. Then we speak of cardinality constraint programming. And here we have another, let's say, visualization what happens. So I just made a little drawing here of a sparsity set. This set C is called sparsity set in this situation in R3. And again, you see the disjunctive structure. You have some union here of n over kappa many kappa dimensional subspaces. And again, we have some almost disconnectedness at certain points. We have lots of kinks there. And although being challenging, this pops up quite naturally in different applications, for example, in data compression or in portfolio optimization. For example, when you think of making up a portfolio of certain assets, but you do not want to have each asset once, but you say, okay, I only want to have 10 different types of assets in order to still have an overview of my portfolio, which is quite natural. Then you are in the setting of cardinality constraint programming. Okay, and another interesting situation appears in rank optimization. So we are then in the setting of rectangular matrices. And again, pick some number kappa between 1 and minimum of m and n, dimensions of the matrix -1, and collect in C all matrices whose rank is at most kappa. Then we are in rank constraint minimization. And again, I'd like to mention some interesting applications here. For example, low rank optimization pops up in machine learning, model order reduction, or what is also quite popular these days is matrix completion. And there I'd like to mention the Netflix problem. Yeah, you are a provider of online films, and you know that your users watched some films, they liked or disliked them. and then you want to fill in these, let's say I do not like matrix such that the rank is low, so that you can divide all the users into certain user groups which are not too small, in order, for example, to advertise in a good, suitable way. And another application I'd like to mention, because we come back to this later, is the so-called Maxcut problem from graph theory. Therein we consider a weight undirected graph, and therein we are looking for a maximum cut, which means we are looking for a set of vertices, and the cut, the weight of the cut is then the sum of the weights of all the edges pointing from vertices within this cut to vertices outside the cut. Okay, this sounds quite technical, but this pops up, for example, in material design, for example, in the construction of the so-called spin glosses. And yeah, we can reformulate this Maxcut problem in a matrix way, and then a rank 1 constraint pops up. Okay, I will also come back to this later. So these are certain examples which shall underline that this is a quite interesting problem class, which is worth of being considered. Okay, and now I'd like to start with the mathematics and speak about asymptotic stationarity and regularity. So I will not need too much tools for variational analysis. Basically, I will only deal with the limiting normal cone and the outer limit of a set value mapping, and these two objects are just defined here on the slide. So recall that the outer limit of a given set value mapping gamma at a certain reference point x bar is the set of all y's, such that we find sequences yk converging to y and xk's converging to the reference point x bar, such that xk, yk is in the graph of the map for each gamma. This is the classical limit in the sense of Pavlov-Kuratowski, and we can easily check that gamma of x bar is always a subset of the set, but not vice versa. If the other inclusion hold, we say that gamma is outer semi-continuous at this point, which is also classical. Some guys call this upper semi-continuous. I will use outer semi-continuous in the same way. So that depends on the literature, but it's a well-known thing one has to when one considers in the literature. And then we have this limiting normal cone. So this definition here is a little different from the one most of you might know, but it's the standard Mordovich normal cone. So we take a closed set A and some reference point x bar, and then the limiting normal cone is the outer limit of certain conic hulls here of cones generated by x minus the projection of a of x onto a, x moves to x bar, and since a is not assumed to be convex, this projection here is potentially multi-valued, and this means we maybe define here a non-convex cone, or a cone which could be non-convex. And for the purpose of completeness, we set this cone to be empty if the reference point is not in the set. Okay, it's the standard Mordovich normal cone. Good, then I'd like to recall a stationarity system for this geometric problem you saw before, the so-called system of M stationarity. This is a variational inclusion you see there, which comprises normal cones to K and C, the derivative of the constraint map G, and the gradient of the objective function. And good for you to know is the fact that if we just consider standard nonlinear problems, then this stationarity system reduces to the standard KKT system. However, this is more general here. So we have something at hand which holds under comparatively mild constraint qualifications at each local minimizer, but as I already said, it is not for free. So in most of the situations we are facing, we need a CQ. You already know this from NLPs. In general, you only get the Fritz-Jones conditions at a local minimizer, and if you have some CQ, then you can ensure that this is a KKT point. And here it's the same. If you have a local minimizer, then under suitable CQ, you get M stationarity. And one of these CQs, quite popular, is the generalized MFCQ, which rules out somehow the existence of singular Lagrange multipliers, which is why it's also called low than zero abnormal multiplier CQ somewhere in the literature. And this corresponds again to the classical MFCQ in standard nonlinear programming. Okay. So now the question arises, and this is the basis of the talk here. If it's possible to find a more general stationarity concept for the problem of interest, which holds at each local minimizer, even in the absence of constraint qualifications, and which naturally pops up, for example, in the setting of numerical methods. So if we have an accumulation point of a certain numerical method, which kind of stationarity condition we can make sure these points always satisfy. And then we ask ourselves, what do we need in order to come from this more general notion of stationarity to M-stationarity in order to figure out a new constraint qualification for this geometrically constrained program. Okay, the first candidate would be the Fritz-Jones system. Yeah, we also have a Fritz-Jones condition for this geometrically constrained program, but that is in general too weak. But here the situation is, if we have a Fritz-Jones point, then we need this generalized MFCQ in order to come up with M-stationarity. And we hope for something weaker if we find a stronger stationarity system characterizing local minimizers. Okay, so that's for what we want to have. And here is a suitable approach to such a stationarity condition. And the first thing you see is it's not a standard stationarity condition which holds at a point, but it demands the existence of certain sequences, which is why we call it asymptotic stationarity. So what do we have here? A feasible point x bar is called asymptotically stationary whenever we find sequences xk converging to x bar, epsilon k, some residuals tending to 0, some yk's. These are also some kind of perturbations which tend to 0 as well, and some multiplier sequence lambda k. We do not say anything about lambda k, no convergence, no boundedness, nothing. And these things have to satisfy along the sequences some kind of perturbed version of M stationarity. So what you see here is we have a perturbation with the residual epsilon k, and we also perturb the input of the normal code to k by this yk. So the iterates xk are allowed to violate the nonlinear constraints g of x in k by a residual which tends to 0. But with respect to C, we demand always that we are feasible. So that's the core idea here. And now some obvious things we can see directly. Each M stationary point satisfies this condition. We just need to set the sequences to be constant and everything is fine. If lambda k is actually bounded by chance, then we can take the limit in this variational inequality there and get M stationarity directly, along with the subsequence, of course. And if lambda k is not bounded, then we can rescale the overall system by 1 over norm of lambda k and take the limit afterwards. And then we come up with some kind of Fritz-Jones type M stationarity with vanishing leading multiplier. So we also get that this is stronger than some kind of Fritz-Jones stationarity. And indeed, one can now show that if we have a local minimizer of the problem, then it's asymptotically stationary in this sense. And for the proof, we just exploit a simple.
So, Patrick, we have a question in the chat.
If it's urgent, yeah.
It seems so. So, would you please show MPGC again?
So the problem we have in mind,
yes,
is this one.
Okay.
So minimizing f and two types of constraints, nonlinear g of x and k, and x and c is abstract.
So, Mr. Zhu, do you have a comment on this, or you want to ask a question? Okay, it's fine. Thank you. So,
okay. Good. So as I said, each local minimizer satisfies this asymptotic version of stationarity, and the proof is easy. What we need to do is we need to consider a suitable penalized version of the original problem. And as the definition of asymptotic stationarity already suggests, we penalize the nonlinear constraints g of x and k. And what we do here is we use the distance to k, and the perturbation with y, which pops up here, is also penalized with some norm squared here. All the iterates need to be feasible with respect to C, so this is included. And the global minimizers of these penalized problems do the trick. So we get the sequences xk, yk from this, and from them we can construct epsilon k and lambda k. So that's easy. Now we need to think about what does it take in order to come from this asymptotic stationarity to M stationarity. And in order to see this directly, I will reformulate these stationarity conditions a little bit compact. And therefore, I will exploit the set value mapping M you see here. And yeah, it basically is related to the constraints of the problem. So it depends on X and Y. And this sum here, you know, it popped up already in the definition of M stationarity, and a little bit it's also related to the definition of asymptotic stationarity. We have the perturbation parameter Y appearing here again. And with this map, I can reformulate M stationarity, so M stationarity of some point X bar, as the negative gradient of F at X bar belongs to M of X bar 0. Easy. And if X bar is asymptotically stationary, we get that the negative gradient of F at X bar is in the outer limit of M at X bar 0. And this set, this outer limit, as I said before, is in general larger than M of X bar 0. If the converse holds, then these equivalences here guarantee that the point X bar is already M stationary. So what we need is that the outer limit of M at X bar 0 is a subset of M of X bar 0, which means M needs to be outer semi-continuous at X bar 0 in order to ensure that asymptotic stationarity yields M stationarity. And that is precisely what we call here asymptotic regularity. So if this map M is outer semi-continuous, X bar is called asymptotically regular. And by construction and by the results I already showed you, we easily get, if we have a local minimizer of the original problem, which is asymptotically regular in this sense, then it's M stationary, because each local minimizer is approximately, asymptotically stationary. Each asymptotically stationary point, which is asymptotically regular, is M stationary. So we are done. This is no mathematics. That's the simple consequence of the definition. The interesting part comes now, because we need to make, we need to find out where in the landscape of constraint qualifications this asymptotic regularity can be found. So is it restrictive? Is it non-restrictive? Where do we are? And I have this slide here with some comparison to other CQs for this problem which apply. And for example, the GMFCQ I showed you before for the cracks, this is just metric regularity of the underlying feasibility mapping. It's much weaker than generalized MFCQ, this asymptotic regularity. And if K is some Cartesian product of non-negative orthant of appropriate size and some appropriately sized zero vector, then we can apply generalized versions of RCPLD to the problem of interest. And in this case, we can show that asymptotic regularity is also weaker than this RCPLD. And RCPLD, the so-called relaxed constant positive linear dependence CQ, known in nonlinear programming, is already very weak.
So Patrick, can you please just explain what much weaker means? I mean, weaker I understand, but much weaker?
Much weaker means that there are some other constraint qualifications in between, which are already, so you have some kind of steps. Good. For example, this RCPLD is also weaker than GMFCQ. Okay. And this asymptotic regularity is even below RCPLD if it actually applies. Okay. It's in some sense on a similar level. Now comes the comparison part. It's somehow on the same level if you just consider a visualization of the map of constraint qualifications with metric subregularity constraint qualification. Both of them, so metric subregularity of the feasibility mapping and asymptotic regularity in the sense I introduced, they are not comparable. And asymptotic regularity is also not comparable to generalized versions of Aberdeen's and Guignard's constraint qualification. So it somehow ranges somewhere at the bottom of the landscape of CQs. And it holds inherently whenever G is affine, K is polyhedral, and if C is disjunctive. So if the data is sufficiently linear in some sense, then the CQ is for free. Good. Now I want to apply this stuff to augmented Lagrangian methods here, to the convergence analysis of them. So what we do is we want to define a suitable multiplier penalty method which exploits this theory, and therefore we only augment the nonlinear constraints, because we already saw from the definition somehow it looks like penalization of the nonlinear constraints. So that is what we do. We perform a standard augmentation with respect to the nonlinear constraints G of X and K, and exploit that the distance, the squared distance to a convex set is smooth in order to see that this partial augmented Lagrangian function here is continuously differentiable. That will be a core idea in the method. And during the method, we also need to control the penalty parameter rho, which already popped up in the definition. And in order to do that, we need to make sure, or we want to keep in mind the feasibility with respect to the nonlinear constraints g of x and k. And at the same time, we want to keep track of the multiplier being close to the normal cone to k and g of x, so that we get this generalized complementarity condition in the multiplier group. And both of these features are measured by this functional v rho you see on the bottom. So we use this functional to control the penalty parameter. And here's the method. So what do? We choose, first of all, a starting penalty parameter rho 0, some enlargement parameter gamma greater than 1, some eta between 0 and 1, a box, let's say, or general non-empty bound set B in the space Y, some starting point x0 and the iteration count is set to 0. If xk satisfies a suitable termination criterion, sorry, then we stop. I will speak about this in a minute. Otherwise, and now comes the thing why it is called safeguarded augmented Lagrangian method, we choose some uk in this set B, which is bounded by assumption, and solve the augmented Lagrangian subproblem. We minimize the augmented Lagrangian function where the multiplier lambda k is replaced by the uk. We minimize the function over C. So in any case, we get the point in C as a solution. And we do not need to compute a global minimizer or local minimizer. What we need to compute is a so-called approximately m stationary point of the subproblem, which means for some residual epsilon k plus 1, sufficiently small, we need to satisfy this generalized variational inclusion here, which is almost m stationarity. If this epsilon here would be 0, then it's m stationarity subproblem, but we can allow here some perturbation. Then we update the Lagrange multiplier. Again, it looks a little bit horrible, but maybe you see what happens. So we have here some element of k, and then we have here some element of the space y, and then we have here the projection of the y to k. So this already looks a little bit like a normal direction to k. So this explains this update a little bit. And then we decide whether we need to enlarge the penalty parameter or not, if we are in the first iteration, or if we have some sufficient decrease with respect to the functional v rho, then we leave the penalty parameter as it is. Otherwise, we enlarge it. And this we do all over again. This is our method. Some words regarding the method. If uk is replaced everywhere by standard Lagrange multiplier lambda k, with respect to the update you saw, then we recover the classical augmented Lagrangian method, but the safeguarding trick with respect to the multipliers enhances global convergence properties. You will see this on the next slide. If we equip the space Y with partial order, which is available in all the applications we have in mind, then it's possible to choose B as a box, and then we naturally choose uk as the projection of the multiplier lambda k to the box in order to keep as close. Was this a question or?
No, I don't think so. No.
Okay. So we project the lambda k basically to the box in order to be as close to the standard augmented Lagrangian method as possible. And only if the lambda k's are actually unbounded, the method changes something. Okay. So this is the safeguarding, and for the termination of the algorithm, you know that basically this multiplier penalty method is a penalty method, so we cannot make sure that the accumulation points of the sequence generated here are feasible with respect to the penalized constraints. So we basically check for feasibility with respect to the nonlinear constraints at the termination criterion. So that's what we basically do. And here is the convergence result related to the method. So what do we need? We need to make sure that the residuals epsilon k within the subproblem solver tend to 0. And we need to consider an accumulation point of the sequence generated by algorithm 1. then we know three things. So first of all, this point x bar is m stationary for the constraint violation. That's the first thing, and this is very standard in augmented Lagrangian methods. The second assertion is a little bit more interesting to us. If we can make sure that x bar is actually feasible to the original problem, then it's by construction asymptotically stationary in the sense we saw before. And if x bar is asymptotically regular and feasible for the original problem, then we end up with an m stationary point. So our method basically computes m stationary points of the original problem under mild assumptions. The problem is this only can be ensured if the subproblem solver does the things we demand. And the question arises, how do we solve the subproblems? And here comes the thing we do. We actually use some kind of projected gradient method, but we equip this one with a non-monotone line search procedure and start with some Barzilai-Borwein type step size. And then we do a non-monotone line search procedure. Okay. The thing is, basically it's a projected gradient algorithm. So in practice, it might need many steps to converge. But the thing is, basically we need to compute projections to the set C here. And in practice, these projections are not that difficult to get. They are not unique in most of the applications, but they are easy to compute because we have closed formulas for one of the elements in the projection at least. So this can be implemented in many interesting situations, and it runs quite well. And the convergence analysis of the method shows that it actually computes approximately m stationary points in the sense we need in the convergence analysis. So we are fine here with this subproblem solver. But it's a little technical to show this approximate m stationary there. Approximate m stationarity. Sorry. Okay. That's for the theoretical part of the method. And now I want to speak about a little bit about numerical results. So I want to speak about two classes of example problems. And the first one is portfolio optimization. So I come back to this one. So we want to make up a risk minimal portfolio. The sigma, which you see there, is the covariance matrix of the available assets. We want to make sure that the portfolio we choose actually generates a minimum return row. And we have some bounds we have to keep in mind for the individual assets in the portfolio, and only kappa many different assets are allowed to be there. So the cardinality constraint comes into play. Without the cardinality constraint, it's a simple quadratic program. So the challenge comes from the cardinality constraint. And we challenge our algorithm by means of a very famous collection of test problems by Frangioni and Gentile. And there are 30 test problems within this collection of dimension 200, so 200 assets. And we challenge the method with 3 different values for the cardinality, namely kappa equal to 5, 10, and 20. And what did we do then for the test? So we first of all implemented the algorithm 1 as you saw it. Initialized it at the origin, and we compare this one to 2 other methods. The first one is just Cplex applied to a mixed integer reformulation. Running time for each problem for Cplex was, I hope I'm not wrong, 30 minutes, but basically Cplex had the value after 2 minutes. And a boosted version of algorithm 1. And what does boosting mean here? So boosting means we start solving the quadratic problem, so the quadratic portfolio optimization problem where we leave the cardinality constraint away, and then we iteratively reduce the value of cardinality by 5. So we start with kappa equal to 200, then 159, and so on. We iteratively reduce it until we come up with the desired level of cardinality, and we take this as a final solution. And in the implementation, we exploit projections not onto the sparsity set. We do more. We project onto the sparsity set equipped with additional bounds. And still for this set, there is a closed formula for the projections available. Okay, so how are the results? Here are some graphics. So what you see here in red is the standard version of algorithm 1. In yellow, you see the boosted version, and in blue is what Cplex does. So what you see is the boosting already helps us very much. And basically, in most of the problems, we are very close to the function value Cplex generates. Not always, but the thing is, our method just needs a glimpse of a second in order to output this, while Cplex had 30 minutes of time to compute it. And that's for the difference here. Precisely, this is for kappa equal to 20, and the situation is even worse for kappa equal to 5. So this is somehow more challenging. And here, what you see is that still the boosted method is in comparison is in position to challenge Cplex, while the original version already struggles a little bit to recover these results. Okay, but we are fine with these because we challenged the problem by methods of nonlinear programming here and ignored each mixed integer structure. So that's for that. And now the other type of result I want to speak about is for the Maxcut problem. So as I said, it works on a waved undirected graph. For technical purposes, we assume that it's complete. Edges which are not really in the graph are equipped with weight 0, and the weight matrix is W. It's possible to reformulate the problem by means of a matrix optimization problem you see here. So we define by means of the weight matrix another matrix L and minimize the trace of L times X. And this matrix X is a matrix whose diagonal is equal to 1. So the all ones vector. X has to be the positive semi-definite, and X has to have rank at most 1. So what's the idea behind the reformulation? You simply take a vector X in your Maxcut problem, which is 1 if your vertex is in the cut and 0 otherwise, and then you take small x times small x transposed in order to define the matrix X, and then you can reformulate the problem in this way. For the implementation of the problem, again, we need some projections, and what do we do here is we project onto the set C you see there, so on the set of all symmetric matrices which are positive semi-definite and whose rank is at most 1. This can be done if we know the maximum eigenvalue of the matrix and the corresponding normalized eigenvector. From this knowledge, we can define the projection. Sorry for that. Okay, and then we tested the algorithm on another famous set of test problems, the collections Rudy and Ising, which were set up by Angelika Wiegele from Klagenfurt. And the first one comprises 130 test problems with 60 to 100 vertices, and in the Ising collection we have 48 problems with 100 to 400 vertices. And what do we get here? Different graphics. We just applied the method, and here you see the percentage of the optimal function value the final output had. And what you see is all problems were solved in some sense to 88% accuracy, and about 100 problems in the collection were solved up to 95% of accuracy. That's for Rudy. And for Ising, we have these results here. So all of the problems here were solved up to 95% of accuracy. To be fair, none was solved to absolute accuracy. But the good thing about our method is that the final output is always a rank 1 matrix by nature of this projection procedure within the subproblem solver, which means the final output here is a rank 1 matrix and can be used for more enhanced mixed integer solution methods, for example, as a good starting point in order to get to come fast to a very good result for each of these problems. So that's a feature which should be mentioned. Okay, so that's for the numerical stuff. And the final 5 to 10 minutes, I'd like to speak about extensions of this asymptotic stationarity and regularity to different types of optimization theory and variational analysis. So what's also possible is to apply this concept, for example, to bi-level optimization problems. And if you make use, for example, of the value function reformulation, so you replace the lower level by its constraints, and the constraint saying that the optimal value is not surpassed, then you come up with a irregular single level surrogate problem, and you can check that in this situation, this asymptotic regularity still serves as an applicable constraint qualification. You can use it, for example, in order to provide convergence analysis again of penalty methods for such approaches to bi-level optimization via the value function. So there is a lot of work to do, and nothing, almost nothing done, but there should be some applications here of this theory. Another thing we did was, again with geometric constraints, but to check out how everything can be done in infinite dimensional Banach spaces, where essentially everything is more difficult. And we can still get some good results if the set C is convex, which means we come around using the limiting normal code, because this one is nasty in infinite dimensions, and we didn't want to touch this guy. And that's why in the setting of convex C and convex K, we can get something. Again, under right assumptions on the data, we get asymptotic stationarity of local minimizers. We can define in a similar way weak constraint qualifications in Banach spaces weaker than Robinson's CQ, which is basically the only constraint qualification of reasonable strength we have there. But now we also have these asymptotic ones. And we can apply this theory to convergence analysis of augmented Lagrangian methods in Hilbert space problems, for example, in optimal control. Okay, we can also generalize the problem structure we had in this talk to non-smoothness of the objective function, for example, and the constraints actually do not need to be of this geometric set constraint type. It can be just the zeros of a given closed graph set level mapping. So the most general thing you can imagine, and still it's possible to write down asymptotic version of stationarity, which holds at all the local minimizers, and from this again, you get asymptotic regularity as a constraint qualification, which now can be used, for example, in variational calculus in order to get the qualification condition to enter that the calculus rules from variation geometry. For example, you might know that the intersection rules, the intersection rule for limiting normals somehow makes use of a CQ. Yeah, you need the CQ there. For example, metric subregularity of a certain associated feasibility mapping. But you can replace this metric subregularity by asymptotic regularity and still get the calculus rule. And the same holds, for example, for the pre-image rule, sum rule for co-derivative calculus, and chain rule for co-derivative calculus. So another approach besides metric subregularity, which can be used. Then a little observation, we can refine this, the result we started with, so that each local minimizer is asymptotically stationary. This can be refined by the following statement. Each local minimizer is either M stationary, or there is a critical direction, whatever this means, and an unbounded sequence of multipliers, such that this asymptotic version of stationarity holds in direction U along this sequence of multipliers. What does this mean? For constraint qualifications of asymptotic type, we only need to consider critical directions. And this somehow relates this concept of asymptotic regularity with the directional calculus for limiting normals established by Crerar and Utrata, for example. And with this directional approach, we can come up with refined sufficient conditions for asymptotic regularity. For example, directional metric regularity. Okay, that's not astonishing, but for example, directional versions of quasi and pseudo-normality are also sufficient for this directional version of asymptotic regularity. And some kind of directional linearity of the constraint data is also sufficient. And we are working at a new variational tool called the horizon coderivative, which explores somehow what happens if the input arguments tend to infinity, which has bad calculus in general, but under additional assumptions on the data, we work here with so-called metric pseudo-subregularity of a given order higher than 1, and then we can calculate something and again get sufficient conditions. So this directional approach is quite promising. And yeah, so that's for the directional observations. And the final things I'd like to mention here are that we can still write down asymptotic stationarity concepts in terms of Frechet or regular normals, so a more restrictive type of normals for problems in Estlund spaces. And here again, a very general problem, we minimize some function phi. This one does not need to be even Lipschitz continuous. Lower semi-continuity is enough over the zeros of a set value map. And in order to get asymptotic stationarity here, we need some additional lower semi-continuity of the data. I do not want to go into the details, but yeah, some additional things are necessary, which are for free in finite dimensional programming. That should be mentioned. And what we get from this asymptotic version of stationarity is a new generalized version of the extremo principle Alex and Boris published somewhere back in the 80s. But we can almost recover this one by this completely different approach. We get qualification conditions for problems with non-Lipschitz objective function. In mathematical programming, this pops up, for example, in sparse portfolio selection or low-rank matrix completion, or, for example, in image restoration, if we have some discontinuous edge-preserving functionals in the objective, we can still apply this theory. We can, again, consider multiplier penalty methods for such problems and get convincing convergence results. And the final thing I'd like to mention for the guys here doing optimal control is that this asymptotic stationarity and regularity can be used, for example, to get optimality conditions for optimization problems in function spaces equipped with sparsity promoting terms. So the things we analyzed here are integral functions which assign to each u, think of that as a control, the integral over omega of u to the p, where p is something between 0 and 1. So this is sparsity promoting. It's continuous, but it's not Lipschitz continuous. And for this, we can still get necessary optimality conditions for problems with box constraints of multiplier type, so including Lagrange multipliers, which is not possible by a direct approach, by standard KKT theory. Okay, and with that, I'd like to thank you for your attention. And yeah, if there are any questions left, I'd be happy to answer them or to discuss them with you.
Thank you very much, Patrick, for a very nice talk. Very interesting results, very many applications, very nice mixture of theory and the numerical algorithms. So, are there questions? Boris?
Yes. Okay, Patrick, is a nice talk, actually, combination of many your recent developments. Indeed, I have actually two questions, two maybe basic questions. First question is about your asymptotic optimality condition, your asymptotic regularity condition, anyhow, everything which is asymptotic or approximate, as you mentioned. Mm-hmm. Approximate means more or less fuzzy to some extent. And then, how, theoretically sounds very, very nice indeed. But how to deal with this approximate stuff in the sense that, say, for limiting conditions and for M stationarity, we have calculus. Point-wise calculus, we can proceed with everything. When you impose this kind of approximate condition, everything like that, how to check them, how to deal with them.
The thing is, in practice, we are more interested in this asymptotic version of regularity because we are on our track to sufficient conditions for them. The asymptotic stationarity concept actually is often only an output of algorithms and pops up naturally for some methods. But you are right, to check them by hand means we have to check whether there is some sequence satisfying something, and this is practically not possible. So the thing we are actually interested in is the part of regularity, which pops up from the stationarity concept. And the stationarity concept, on the other hand, directly cannot be checked, but we can find sufficient conditions for it. And these can be checked in terms of initial problem data. For example, if you think about this quasi-normality and pseudo-normality, which are quite weak, but you can check them actually. So you may think of this not as directly applicable, but a new approach, let's say, to optimality condition, constraint qualification, and variational calculus. So that was our initial idea behind generalizing this from NLPs to geometrically constrained programs and more general types of optimization problems. I hope this answers a little bit your question, Boris.
Sure. That's fine. And Patrick, I have a question, a more specific question regarding your augmented Lagrangian stuff. First of all, you can cover non-polyhedral problems here, right?
Yeah.
You can cover non-polyhedrality, right?
Yeah.
Okay, then what about rate of convergence? If you have convergence, actually, what about convergence itself, and which kind of rate you can provide by using this asymptotic approximate stuff?
So the thing is, we never checked that. But the thing is, if you have some kind of metric subregularity constraint qualification, you have the modulus available, which somehow for sure gives you some rate everywhere in this. So for standard augmented Lagrangian methods, you can show a rate under a constraint qualification like MFCQ, which is metric regularity. You have the modulus available and you can show something. Asymptotic regularity does not come with a modulus. So I'm skeptical whether one can show actually a rate of convergence here. So I would say this is not possible, but it's only a guess. It might be possible, but yeah, because the property does not come with a modulus, I don't think it's possible.
Yes, that's actually a very interesting question to think about. Actually, we are looking for superlinear convergence, at least for linear convergence. And again, I didn't get this from your talk, but I think it's a very promising area of consideration. And then the final question, again, regarding augmented Lagrangian methods. Do you assume any kind of uniqueness of Lagrange multipliers?
Not at all.
Not at all.
Not at all.
But if you assume uniqueness, could you proceed better?
I don't know. We never thought about this.
Okay, that's actually, as you know, that I think in all the results about augmented Lagrangian, there are uniqueness assumptions. But under some kind of regularity or whatever, this condition, we can get superlinear convergence. And superlinear convergence, what actually is kind of certification of the algorithm. And that's what my understanding, that would be nice to consider your conditions, your theoretically developed stuff, and to see all the stuff together, especially for non-polyhedral problems.
Yeah. The thing is, what we did was a global convergence analysis, and the results you have in mind are, I think, local results, which are based on maybe some second order condition or something like this.
Yeah, but I think not only local, now we can globalize. I think local, of course, to begin with, but then we have globalization. There are several tricks to globalize these local conditions. But you're right, second order conditions are there, and it is essential part. But anyway, okay, we can talk more privately, right? And then thank you very much for your talk and for your answers.
Thanks for coming. And
thank you,
thanks for your questions.
Thank you, Boris. Jonathan.
Can you just show the main algorithm again?
Of course.
Okay. Okay, so I think this is fairly standard, but the idea, this mu seems, you know, in the statement of the algorithm, this mu is completely disconnected from lambda, right?
In practice, it's the projection of lambda onto
Right.
B.
But you analyze
not
almost like it's just a penalty method. You don't really assume it.
Yeah, you can choose U to be 0, and then you get the standard penalty method. Yeah.
Okay, but you just, the important thing is boundedness. That's what makes it all fly, right?
Precisely.
Yeah, okay.
That's the main idea of the safeguarding.
Right. But it just looks weird in the abstract statement of the algorithm because like mu and lambda are like disconnected, right? But,
Yeah.
Yeah, okay.
Thank you. Other questions?
Actually, I'm sorry, after Jonathan talk, I would like to ask you, what precisely do you mean by safeguarded? It means, what is the difference between standard augmented Lagrangian?
In standard augmented Lagrangian, your lambda case can be unbounded.
Yes.
Which means in your convergence analysis, you may run into the situation where you have to consider lambda k to be unbounded, and then there are cases in your convergence analysis where you cannot proceed. But here you are in the situation where in the convergence analysis, basically the behavior of the sequence uk is interesting, and uk is always bounded. So in finite dimensions, you can come up with the convergent subsequence, and everything is fine.
Okay, the issue is about boundedness, but I think it can be overcome even in what do you mean standard, but kind of Rockefeller type augmented Lagrangian. I think boundedness can be overcome, but anyway, it's more
not for non-convex problems. No, it's not so easy.
Yeah, it's the non-convexity that
yeah
you lose all the niceness of the
yes.
something. Yeah.
So you will have to assume some coercivity, or like to guarantee it, or just to ask.
Yeah. Okay. Thank you.
Thank you, Boris. Are there other questions? So I have a question. Oh, yeah. So, okay, go ahead, Mr.
David. Yes. Patrick, what if it's a binary variable?
Which one?
X. X here was between 0 and mu k, right? It was a bounded. What if it was a discrete variable? Will this be applied, or?
So the thing is, up to a certain level of discreteness, for example, this portfolio optimization problem with cardinality constraints is a mixed integer problem. Then you can apply the technique and it works quite fine. But for example, I also did some experiments for variables of the type x0 or in some interval, which is far away from 0. So where you have a large gap in between, and there the method basically struggles to do anything reasonable because it's somehow too disconnected. So one cannot say by chance it's absolutely not applicable to mixed integer stuff, but in general, it's not designed for that. The thing is, you have to be in position to make these projections, and then still you have to rely on some connectedness of your feasible set in order to get something reasonable. At least that's the thing I can tell you.
Okay, thank you. Yeah.
Thank you.
I mean, it is a disjunction, right? I mean, so on the surface, it looks like it applies, but
in practice, it depends on the problem structure.
Yeah.
So we have very nice experiences for disjunctive problems and for this Maxcut stuff with matrix ranks. But yeah, there might be other situations where it is completely outplayed by simple other methods.
Okay, thank you. Are there other questions? Then I have a question. So can you show again, or can you just describe the type of convergence you have for this algorithm? So this is a local result, a local convergence result.
No, it's a global convergence result.
Okay.
So the thing is, what you first need is a subsequence which converges to some point.
Yes.
And you know that the point is stationary for the constraint violation. If the point is feasible, then it's asymptotically stationary, so it satisfies the definition. So the method constructs by design these sequences xk, yk, lambda k, and epsilon k, which pop up in the definition. And if you then know that this asymptotic constraint qualification holds, you can directly deduce that your limit or your accumulation point is m stationary.
Okay, but we're still talking about the subsequence.
Yeah, we do not speak about the overall sequence.
Why not? Can we make the whole sequence converge?
It depends again on the structure. If you have some quadratic regularization term at the objective, potentially something is possible, but in general, I think it's not.
What about the critical series property?
Okay, that's potentially possible, but we did not touch this one.
Okay. Yeah,
But you are right.
that's a natural question. Yeah, I mean,
that's the popular things from this century. Yeah.
Yes. No, but yeah, okay.
Are there any results relating this property to augmented Lagrangian? Because I never did
Yes,
some
yes.
details there.
Yes.
Okay.
So like even more general to general primal dual methods.
Okay.
ADMM. So yeah, so everything in the non-convex case. Yeah.
Okay.
Convex yes.
Would be of course nice to investigate this because the class of functions there is large. Yeah.
Sure. Okay. Yes, I agree. Okay. Are there other questions? So then let us stop here. It was a great talk. We had a great discussion. Thank you, Patrick.
Thanks everyone for coming.
I just want to announce that you will post the slides and the video on our website, and that our next speaker will be Matthew Tan from Melbourne. Yeah, next Monday, same time, 3:30 Vienna time. So have a nice week. See you next Monday. All the best. Thank you, Patrick.
Bye-bye, everyone.